Hi everybody, this is Abe from B351. In this video, I'm going to be modeling an algorithm for solving constraint satisfaction problems using backtracking. First, let's quickly define a constraint satisfaction problem. Constraint satisfaction is the process of assigning values from a set of possible values to a set of items, which have certain constraints about how their values must or must not be related. Generally, most constraint satisfaction problems will have some data structure that maps items to assigned values, and some way of verifying that each constraint is satisfied as items are mapped to their assignments. One constraint satisfaction problem might be selecting cards from a deck, such that the total of their values must be 6. As a matter of fact, there are many possible solutions, but if we specify further that the first card must be a 2 of spades, then we end up with only 4 solutions. The second card must be the 4 of spades, diamonds, clubs, or hearts. On the other hand, if we assign the first card to be the 7 of diamonds, there are no assignments of the second card that allow our constraint to be satisfied, and so that assignment contradicted the constraints of our problem. Here, we're going to be working with a rather simple tile coloring problem based on the classic 4-color map problem. Our items are a subset of the tiles on a grid. Some tiles on each grid might be blacked out from the start. And our values are 4 colors: red, green, blue, and yellow. Like in your homework, we represent our value here as a dictionary, whose keys are points and whose values are colors. We also use 2 special values, empty and black, in addition to our valid colors. These allow us to initialize squares differently depending on whether or not they are blocked off in the map file specifying the problem. As I mentioned before, most constraint satisfaction problems will have some data structure that maps items to assigned values. Our constraint is that no 2 horizontally, vertically, or diagonally adjacent squares can have the same color assignment. The heart of the backtracking algorithm is the idea that we may not have enough information to assign a specific value to an item at the beginning, but rather that we might need to try out several different values, none of which violates our constraints, to see which ones allow for a solution later on. Many of them will result in unsolvable states, where another item will have no possible values. If some assignment of a particular item does not allow for a possible solution later on, we have to catch that contradiction, backtrack, and try another value for that item. The algorithm is recursive. That is, after making a conjecture as to what one item is, you then need to conjecture about another item. Only when you find a contradiction, or the entire problem is solved, can you end the recursion. My implementation distinguishes between these 2 cases by using a custom exception called contradiction. If a contradiction is raised, then the last assignment must have been invalid. If the function returns without error, on the other hand, then the entire map has been solved consistent with our constraints. However, other solutions might use different return values for success and failure, or keep track of a variable for whether or not certain patterns result in contradictions. This last option can be extremely tricky, but implemented well, it might optimize your solution significantly. Let's start coding. As you can see, color map is not much more than a simple recursive function. Don't worry about reproducing my particular way of writing it. It's the logic that matters, not the implementation. First, we choose a square to focus on. If there is no possible square, then that means that the entire map has been colored and we have solved the task, so we return without error. If there is a square, then for each color our square might take, we try that color and see if it results in a good solution. If it does, then we return without error to indicate that we have solved the board. If it results in a contradiction, then we undo that assignment and continue along our iteration, trying other values. If none of the possible values worked, that means that we can't assign any value to this square, which means that we can't satisfy the constraints we're operating under given the prior assignments, a contradiction. Next, let's look at our choose_square function. We'll make a smarter implementation later, but the minimum that is required here is to select any square that is not already assigned. So I simply iterate over the squares in the map and return the first one that is still empty. Notice that if no square is still empty, we explicitly return none to indicate that the board has been solved. Technically speaking, a function without an explicit return will return none anyway, so this is really just a way of indicating our behavior to a reader. Next, let's look at how we determine which colors are possible for any given square. Right now, our algorithm doesn't keep track of which colors are valid for which squares. For many constraint satisfaction problems, such as this one and your homework, it can be significantly more efficient to keep track of which assignments are valid, but as this is a simplistic implementation of the algorithm, I think it is reasonable to organize our logic this way, recalculating which assignments are valid every time we investigate a square. As an exercise, you might be able to extend your logic to keep track of the possible colors for each square in a few different ways. To check which colors are possible for any given square, we simply have to find the colors that are not assigned to any of its neighbors. I do this by using a Python list comprehension to get a set of the colors of the neighboring tiles, then iterating over all of the valid colors, yielding whichever ones are not already assigned to a neighboring tile. This yield operator allows you to iterate elsewhere over the possible colors for a tile without storing all of those possible assignments in memory. It's not really necessary here, but when you have a very large possibility space, it can save a great deal of memory. By the way, if you'd like to build your programming skills a little, re-implementing the getAdjacentSquares function using a different technique would be excellent practice. Now let's quickly go over the color square and erase square methods. Because this implementation only keeps track of minimal information, they are rather simple. And this is actually all of the code that we need to color maps. Let's watch it run on some of our demos. This certainly works. However, our method for choosing a square to color is not particularly clever right now. Programmers generally select a heuristic for which square to color next that will minimize the time it takes to find the solution. Two common heuristics are the most constrained heuristic and the most constraining heuristic, and they both seek to minimize the number of possibilities that must be considered. The most constrained heuristic selects the tile with the most constraints currently on it. In this problem, the one whose neighbors include the most colors, and assigns values to it first. This minimizes the branching factor in the short run. Fewer values will need to be considered for each tile, and so the overall number of possibilities considered will be lower. Significantly, it also tends to quickly reveal invalid assignments by investigating the most logically restricted items. The most constraining heuristic, on the other hand, chooses the item that imposes the most constraints as the one to give a value to next. In this problem, that would be the tile with the most unassigned neighbors. The intuition behind this strategy is that it most dramatically minimizes the size of the entire possibility space for later stages. This ends up making it much less frightening to search the entire possibility space for solutions. However, in this problem, it would result in multiple highly constraining tiles being considered without regard to how compatible the assignments of those tiles might be, and so it is not very efficient. It is possible to combine the considerations of the most constrained and most constraining heuristics, but that involves challenging judgment calls. It is not easy. If you want to go down that route, I would advise you to think analytically about the structure of the task and its search space to work out which heuristic would help you zero in on solutions the fastest. For the time being, we're going to implement the most constrained heuristic for this problem. The first step of this is to make a function that gets how many constraints each square has. In this situation, the constraints on each square are that it cannot have the same color as the squares horizontally, vertically, or diagonally adjacent to it. This means that a square has one constraint for each different color one of its neighbors has, and that adding another neighbor of the same color does not add another constraint to the cell. So our function to get the number of constraints on a tile counts the number of different color assignments its neighbors have. To do this, I use a Python set object like before, being sure not to count either black or empty tiles, but there are several different and more efficient implementations of this logic. In the event that we have as many constraints as valid colors, none of them are going to be able to be assigned to the tile, and so I raise a contradiction. Note that here I'm counting squares that are blocked off or already assigned as having -1 constraints for sorting purposes. Now, to choose a square according to this heuristic, we need only order the squares by how many constraints they have, take the most constrained square out of all of those, and then check that that square is empty. If the most constrained square is non-empty, then all squares are non-empty because non-empty squares are sorted after all empty squares, and so the board has been solved. Thus, we can return none for our choose_square function in that event. Now we have a full implementation of the backtracking algorithm, including a heuristic for choosing the next square to color. I would suggest that your next step in improving the solution would be to implement some sort of forward checking, preventing assignments that would invalidate a square from being made. If you want to try implementing this, which shouldn't be terribly difficult, I think that would make an excellent exercise. Thank you very much for watching this video. I hope it's been helpful for you. If you have any questions at all, be sure to ask Saul or one of us UIs. Best of luck to all of you as you work on your Sudoku solvers.